Hello, welcome back to this class where we are discussing about the corresponding thermal degradation of a very simple salt what we know and what we use from our school days, which is your copper sulphate pentahydrate, and we want to see the corresponding plot, that means Dtg plot we want to see. So, if we know nicely this particular Dtg plot and if we can analyze this thing very correctly, you should be able to mass loss characteristics like this. What we have seen most of the time we draw like this, and is a very simple one, as we have seen in case of, and we have analyzed that for also your calcium oxalate and your magnesium oxalate sample. So, what we have seen that we have the different steps, and these steps are for the corresponding elimination of the different number of your water molecules. So, if we have this particular copper sulphate pentahydrate, so what we find that we have step number 1, step number 2, step number 3, step number 4 and step number 5. So, 1, 2, 3, 4, 5. So, what is the corresponding step? So, if your sample is very pure and if we go for the corresponding elimination in this fashion, that means when your temperature is just above 100. So, it is just above 100. So, you have this corresponding 120, then 40, then 60, 80 and 120 degree centigrade. So, when we have this particular one, that means when you have just 100 degree or 120 degree centigrade, we get the corresponding first wet loss. And so, we have the corresponding wet losses, and these wet losses are such that we can have two equal steps. That means, you have this, that means you have in this particular first step is that you have initially you just go for loss of 2 water molecules. So, first step will corresponds to the 2 water molecules. So, what we should know now for this particular information, that in a stepwise manner your all the 6 things, that means you have 5 water molecules, as we have seen that you have 5, but all these 5 water molecules are not same. That means their entrapment within the crystal lattice is different. So, their connectivity within the solid lattice is different. So, that is why all 5 are not going away immediately at a particular temperature, and also it is not of your typical lattice water. What we know that the dehydrated sample, because what you expect that if we go like this, like your calcium oxalate or magnesium oxalate, that means if we go for as typical anhydrous copper sulphate. So, at some point we should get, if all 5 water molecules are eliminated in a single step, we should go for the corresponding one as your copper sulphate pentahydrate species. But the first step we have the corresponding loss of 2 water molecules. So, what we get at that particular point, and if there is a good baseline, but we do not have that baseline, good baseline, that means the stability of that particular step is very less. That means the stability of the corresponding species what is formed over there, what is that, which is nothing but after removal of your 2 water molecules, we remain with only copper sulphate trihydrate. So, this copper sulphate trihydrate has not much stability. So, it immediately go for its loss again for another 2 water molecules. So, these 2 are almost consecutive, but at 2 different temperatures. So, this is being completed. So, it is starting from say around in the so it is starting basically the loss is starting around 80 degrees centigrade, and it is basically complete at 120 or 140 degrees centigrade, where 4 of the water molecules are going away, and those loss of 4 water molecules will also correspond to a loss of minus 14.3796% and minus 14.2034%. So, is a 14 percentages of loss in these 2 steps will correspond to this particular, that means by weight it is 4.5296 and 4.4741 milligram. So, these two are we are losing. Then what we get, we have the corresponding one for your loss. That means the next step will definitely be your corresponding percentage in terms of half of the same. So, if first one is 14%, second one is 14%, the third one will be 7%. So, you have in the first step the 14% weight loss, then the another 14% weight loss. So, what we get at this step is the monohydrate copper sulphate monohydrate, then you have the anhydrous copper sulphate. So, at this point when you reach here, we get the corresponding anhydrous copper sulphate, and this anhydrous copper sulphate what we get basically above 250 degrees centigrade. So, if we want to make a sample of copper sulphate which is anhydrous in nature, because it is blue in color, this particular in the solid state also, but anhydrous thing of this copper sulphate is colorless. So, which we get around 250 degree centigrade. So, at 250 degree centigrade what we get as the colorless copper sulphate, which can be considered as a anhydrous one. So, if we take this anhydrous copper sulphate and keep in again in some moist environment or in moisture containing some environment of air, it will again trap those water molecules and it will again go back to your pentahydrate sample. So, what we see now, the stability of this copper sulphate, that means anhydrous copper sulphate, which is not so easy to get, because in most other cases like your anhydrous calcium oxalate or anhydrous magnesium oxalate, most of the time we get that around 140 or 150 degrees centigrade we get the anhydrous one. But here we have to reach around 180 degree to lose 4 water molecules and to get typically anhydrous one which is above 260 degrees centigrade. So, only above 260 degrees centigrade we get the corresponding anhydrous copper sulphate sample, and this anhydrous copper sulphate sample is pretty stable from this temperature to say about 600 degrees centigrade. So, till 600 degrees centigrade we do not see any loss of mass from the copper sulphate sample, but when we heat the sample at 600 degrees centigrade we see a little bit of monotonous weight decrease from here, and which is little bit broad also, and we go up to say 780 degrees centigrade. So, this is your 780 degrees centigrade. So, till 780 degrees centigrade we have some reasonable weight mass loss which is corresponding to 32% of the weight what has been taken, and in terms of milligram it is 10 point some amount, 10.1187 milligram of weight loss, almost 1/3 of the sample what we have taken for the measurement. So, this particular one if we correlate nicely with that of our sample, and we have seen that we have SO4 2 minus as the anion, but when we go for the solid state heating. So, the solid state heating of this sample of this copper sulphate pentahydrate basically giving us the loss of SO3. Now, SO3 will be losing from here, as we have seen in one of our previous example of your ferrous sulphate heating, that SO3 is the most useful component what we get, that means sulfur dioxide elimination from all sulphate samples are very easy, particularly at a very high temperature which is above 600 degree centigrade. So, if we get, that means this is the case of loss of this SO3. Then once we get SO3 loss from your copper sulphate, we immediately think of that okay, this SO3 is going out from one copper. So, we must have copper oxide over there. So, end product can be your simple copper oxide in your hand, but is not like that. So, what is your end product for this particular type of thermal degradation? So, whether cupric oxide will be your end product or not. So, we keep on heating the sample from your this 780 degrees centigrade, because it started from 580 to 680, this span basically over 200 degrees centigrade. So, throughout this 200 degree temperature rise, your SO3 elimination is complete. So, if we go beyond that temperature, so around 900, that means around 80 degrees centigrade, there is a very small wet loss, which is roughly about 3%. So, 3% wet loss, and the amount is also only 1 milligram in the range, and then the amount what is remaining over there at 1000 degrees centigrade, we can correlate that what is the remaining sample by looking at the weight left on the pan, what is they have taken for the heating. So, the weight of that particular thing, that means the empty pan weight and the residue of the sample what is formed over there by this particular heating process will tell us the residue weight is 9.0235 milligram, corresponding to a percentage of around 28%. So, that 28% weight remaining as residue on the crucible is not due to your CuO, but is due to your Cu2O. That means, is during this particular heating process, the sample has an inherent tendency to give you the corresponding form as the cuprous oxide, and this Cu2O basically going for its self reduction process with the elimination of half of the oxygen. So, if we consider, so that particular step can also be very nicely detected in this particular plot, and O2 elimination from CuO, if it is formed as a very transient species, because we are unable to detect the formation of CuO as the end product of heating of copper sulphate pentahydrate. So, it is your Cu2 which is your real end product, what we get from this particular heating process. So, this real end product. So, this real end product is going for, so the conversion, that means this conversion from cupric oxide to cuprous oxide is basically a reduction process. So, at high temperature we go for this typical reduction. So, no reducing agent is required, it is only the elimination of O2 gas. O2 itself is going out from your sample, giving rise to your Cu2O. Because this particular Cu2 is also a very good and useful species, it can be a catalyst also. So, from copper sulphate pentahydrate we know all the different steps, and we can also some good idea how this particular one, that means how this particular one, that means the monohydrate has some stability, and this monohydrate can be prepared also, and this monohydrate, this water binding is completely different with the involvement of the sulphate. So, that is why we get this particular one, that means this water molecule is completely different from that of the 4 other copper which is present and which is going away from this. So, what we can consider, that we know that the copper has a typical coordination number of 4. So, if 4 of them are of same type, we put 4 water molecules around this copper which are of one type. So, we put this as a one type water molecule over there. Then we have to put, or we put it also that another water molecule and the sulphate anion, and which are also entangled with that sulphate. That means, some close association of this water molecule with that of your sulphate will give rise to some extra stability to this particular water which is lost in the third step. So, this gives us a very good idea about the corresponding thermogravimetric analysis for identification as well as the characterization of a sample which is well known to us. So, any other sample such as your food material can also be very nicely analyzed this by this particular technique. So, the decomposition of your sucrose sample. So, the decomposition of your sucrose sample at 10 Kelvin per minute in air will give rise to a plot like this. So, your TGA plot will see or say that it is basically stable till 220 degree centigrade, where we have. So, the sucrose can be dried enough for this particular one case. So, and beyond that we have a continuous mass loss for a typical wet loss of these things, that we can have a corresponding residue after this complete burning. So, you have this, that means this particular part we can separate out with these two horizontal line we can extend. So, this is one horizontal line. So, but you have the basically this sort of inflection point. Actual plot is like that, but we can break into this as the horizontal line and these steps basically. So, we can pinpoint this temperature, we can pinpoint this temperature also for this particular inflection point. What is your 504 degrees centigrade at this particular point, above 500 degrees centigrade. So, this particular step, which is basically a 63% wet loss starting from 233 degrees centigrade. So, this is a typical loss of your sucrose burning process. But what sort of this burning, whether it is a exothermic or endothermic, just now we have seen in some other example that when we have the plot which is in the upward direction, the derivative plot, we call it as the exothermic, heat is being released, energy is being released. But if we consider that corresponding derivative plot of this, so this particular plot change of this is typically the corresponding thing, that means your endothermic melting process, or we sometimes call it as a typically the food engineers basically say that the food chemistry for that, which is caramelization. So, this caramelization process is taking place due to the melting process when sucrose has the melting the melt condition. So, the sucrose melt basically give us the corresponding caramel what we use for making cake, making pastry and all these things. So, which are very useful process, at which stage the exothermic decomposition and combustion also occurs. So, after that also, so this is your endothermic peak, and when we try to detect this particular one, that means at around 500 degrees centigrade. So, followed by an endothermic caramelization peak, at which stage the exothermic decomposition or combustion occurs. So, what we get again from that same book, we get this plot, that means your sucrose can be characterized in terms of its endothermic or exothermic peaks depending upon its corresponding melting process. So, what we see now that if we have another material, that means maize and corn starch, so it is a mixture. So, not only the pure sample, the sample quality, the sample purity also can be checked. If we find that this temperature for this mass loss, what we know that the corresponding determination of melting point is also a very good technique for identifying the purity of the sample. Similarly, the boiling point also is a very good technique to determine the corresponding purity of the sample, in such a way that we now see that the TGA plot, the TGA curve of a mixture of maize and corn starch and crystalline sugar. So, you have the starch and the sugar. So, if we have the corresponding mixture of these, that means you have this, as we have seen that above 200 we have the caramelization step for sugar. Initially we have the loss of moisture from starch. So, starch has huge amount of moisture. So, when the mixture is being heated, basically all these three all are the corresponding component of the food material. So, the corresponding TGA plot, the characteristic TGA plot is also tells us that what sort of thing is happening and what sort of mixture we have. So, first is the moisture loss, then the caramelization process, then this particular step what has been also deconvoluted in terms of some straight line slopes of these. So, one straight line, then the second one is a very direct one which is a perpendicular one, and then some slope corresponding to the baseline thing. So, baseline has been drawn over here. So, which is the basic main decomposition step of corn starch, and which is also about 25% of that decomposition starting from your 309 degree centigrade is the midpoint. Inflection point as well as the corresponding midpoint is here. So, midpoint temperature for your decomposition of starch. So, not only the burning of the carbon particles or the carbon paste or any other carbon powder, but we can also analyze the corresponding food samples, very nice food samples, sometimes the powder samples of all these can be analyzed. And since we are processing for these things, making cake, making biscuits, making pastries and all these things, we require to have some temperature, that means the oven temperature. We set some oven temperature and most of these things around 200 or 300 degrees centigrade, but if we go beyond that, what sort of other thing can happen during the corresponding making of the cookies, the homemade cookies or the biscuits, that we can find out from your TGA plot of the food samples. So, the quantitative analysis now, if we can go, that the typical quantitative analysis, if we see that the derivative plot will then be useful. So, the derivative plot, whether it is a exothermic plot or endothermic plot, what we see that for this typical one, so if you have that from 0 and is the when it is derivative plot, that means is the milligram per minute, that means if we go for in the time axis, this is your now time axis. So, if your derivative plot, the instrument directly records the thing. So, the Dtg plot is like this. So, from 0.0 in the negative direction, that means the mass loss is taking place for this particular process, and if we go for its corresponding integration using the baseline of this particular point. So, if we have the first step, then you have the second step around 300 degrees centigrade. So, this is the temperature above this axis is the temperature axis and then the time axis. So, it is almost the monotonous increase, that means whether you go for the time axis or you the temperature axis. So, around 300 you have this particular peak and this peak is being shaded, and how you draw the baseline, because originally you have this 0 baseline and this 0 baseline was like that when we have started our process, that means when we start our recording the thing from 0 degree centigrade. So, we go for this, but this particular plot, that means this particular crest, the top, this one, that means the depression is this particular point of say temperature. We see that when it is going up, it is not reaching to your original 0 line. That means sometimes it is not so easy to get that your plot is touching the baseline before the start of the plot, and at the end also it is going down again to the same one. It is not happening to any kind of plot. What is happening over there in the real sense is that when we go for this thing, because when we reach this, when we try to go back to your baseline, what is happening that your this temperature is nearby, this temperature is close by. So, this temperature will be reaching. So, your recording for the second peak is also commencing. So, the commencement of the second peak immediately after the first one will not allow the baseline to touch the 0 line, it will be like this. So, when after this also again a very sharp line, it is reaching over here, but at this point also it will not again go back to your 0 line, because you have a third point. So, if you have the third point, so this will go. So, when you go for the baseline type spline we get, so is it not this particular exact baseline, but instead of that we smoothen the plot, that is as if this plot is not there. So, if we smoothen the plot and we see the line, so this if we make this as a hand drawn also, and sometimes the computer software can take care of this thing to draw it in this particular form. So, if we go like this and this particular plot is basically this, and then the shaded area is because of this corresponding area due to the particular thermal process. So, instead of using the step evaluation of TGA curve, because we know that the TGA curve can have the different steps, a mass loss can be quantified, because we are looking for the quantification, that means the actual amount of mass loss what is being taking place from your derivative plot. By integrating the Dtg peak, that corresponds to the TGA step. So, your TGA step was there. So, you have the original TGA step, and corresponding to that TGA step we have the corresponding derivative one, and the area under this derivative plot is then quantified for this corresponding mass loss, and which we try to correlate with your Tg plot. So, your data you have in your hand, and this data you can also quantify in terms of its corresponding area determination. So, this area determination will also tell us in such a way that if we go for this derivative plot. So, this derivative plot will give us some information in this regard, that how you get this derivative plot and how we can correlate this with that of your thermogravimetric plot. So, the next case we will just go for your corresponding another technique is your not a differential thermogravimetric analysis, but a derivative one is also not, is a differential thermal analysis, is another type of analysis where we will concern or will focus our attention on the temperature change. So, if we can monitor the corresponding temperature change of the sample as well as the reference, we can have some plot for that, and as a result what we are just basically looking for this temperature change is the corresponding heat effects, because we are heating the sample as well as the reference within the same furnace. So, we will now try to monitor the corresponding heat effects, and how the heat effect, that means how much heat we give to the sample or the reference, is responsible for the corresponding change in the temperature. So, what we find here for the differential thermal analysis, it involves the heating or cooling test of the sample and the inert reference material, both of them we place inside the furnace, because both of them are nearby within a difference of say 1 centimeter only. So, they will remain in identical conditions, and while recording any temperature difference between the sample and the reference, we will try to monitor. Then this differential temperature is there. Now, this temperature we call as the this differential temperature when we keep sample as the reference in the furnace, which is different from your differential Tg plot. So, this differential in temperature is then plotted against the time or against the temperature, because in Dtg plot we are talking in terms of the corresponding mass loss, but here we will be talking in terms of the corresponding difference in temperature between the sample and the reference. So, now if there is any change in the sample which led to the absorption or evolution of heat between these two, that means the sample and the reference. So, if you have the changes there, then the heat can be that the corresponding absorption, whether you have exothermic process or an endothermic process, can be detected relative to an inert reference, that you have the inert reference and that reference sample is also being heated. You have the simple reference material, it can be your like that of your crucible material like alumina, it can be your alpha alumina also, and that alumina is also heated. So, how the temperature rise can take place for alumina sample as well as your sample under test. So, we get these two things, that means the heat effects what we find, these basic heat effects, and these heat effects are basically associated with several chemical and physical changes. So, there are changes which can be chemical or physical, and we have to plot as a function of temperature and time or temperature or time, okay, not and is or time. So, function of temperature or time we plot these, and these temperatures are there. So, what we try to find is that the heat effects. So, what we basically look for any reaction, we now have some idea about the delta H values, because we know that if there is equilibrium, we always talk in terms of the corresponding free energy change of the reaction. That means the delta G value, now we will talk in terms of the corresponding delta H value, and this delta H value can be both way, that means it can be exothermic or it can be endothermic. So, basically what we now look for, that the heat effects are there, sample is taking heat for a particular type of process. That means, it can be your crystallization, it can be your decomposition, it can be your oxidation, or it can be your reduction. But what sort of this heat effect we can see for these processes? So, any change of these samples can either be exothermic or endothermic, can be detected relative to an inert reference material. So, what we see that these DTA curves can provide data on the transformations, several transformations. These transformations can be exothermic transformations or endothermic transformations, and such as you have the glass transitions, you can have the crystallization, you can have the melting, you can have the sublimation. So, all these processes can be monitored by DTA, that means the corresponding thermal analysis, differential thermal analysis, and like that of your Dtg plot, the DTA also can give rise to some area under the plot, that means is also a peak type of thing. We can monitor the corresponding enthalpy change and not affected by the heat capacity of the sample. The sample heat capacity will be ignoring that, will not consider the corresponding sample heat capacity, but we are looking for these particular processes, and we basically monitor these in terms of the corresponding differential method. And sample temperature, now what temperature change? It is the temperature change of the sample will be continuously compared with some reference material or the reference material sample as the corresponding reference temperature. So, the reference temperature is being monitored with that of our reference temperature with that of our sample temperature if we heat both of them together inside the furnace. Okay. Thank you very much. So, next day we will continue again from here.